Hi and welcome to one of Arm's AI Tech Talks, bringing you the latest in AI trends, technologies and best practices from Arm and our ecosystem. Make sure you subscribe and hit that notification bell so you don't miss any of our upcoming talks. And don't forget to view the playlist too in the link above. I hope you enjoy this Tech Talk.
Hello, good morning, everybody, or good afternoon, wherever you are joining us from. We're delighted to have you here today. We've got Imagimob in the house, and I understand they have a giveaway, which Johan will tell you a little bit more about that. But I'm fresh off TinyML Summit from last week. I don't know if any of you all attended, but it was pretty amazing. Great to see all the companies that were delivering solutions and papers. It was exciting. It was my first face-to-face since the pandemic, so that was fun. It was great to see people in person. And Imagimob were there. I got to meet Anders, the CEO of Imagimob, and it was great to talk to him. So, and he may pop in here. I do see him here, so he may have a little cameo on this Tech Talk. So, but before we get started, I want to tell you how you can find us on Twitter. So, and Johan, if we go to the next slide briefly. So if you want to tweet us at Arm Software Dev, that would be great. We might give you a little shout out and a follow from Arm developer account. You can find all these talks on our software developer YouTube channel. This talk will be available shortly after this presentation. You can also find a lot of our other tech talks in case you missed some of the amazing companies that are doing these TinyML and solutions, ML solutions on ARM. We've got like 24 hours of them at this point, and you will learn a lot for sure. And then for our upcoming tech talks, we have some exciting other topics coming up. So we've got Keekso coming. They have been in our partner program for a couple of years. Love Keekso. They've always got something new to show you. And they'll be talking about our new ARM virtual hardware and what they've done with it. So that's pretty fantastic. We have EMSA coming. They have done some really cool things on our new Ethos U55. So you don't want to miss that. It's pretty impressive. And then we've got Noda, who is coming to talk about how to design neural models, a hardware-aware approach for doing that. So anyway, thank you for all the comments on chat. Everybody needs a Raspberry Pi 4. I hear they're hard to get your hands on right now, but you never know. Hopefully our supply chain issues will ease up a little so we can all have a R Pi. So I will stop talking because you didn't come here to listen to me. I'd like to introduce Johan Malm from Imagimob. Hey, Johan, how you doing?
Hello, Mary. Nice to be here.
Great to have you here.
Be here again, I would say.
Yes, this is our second Tech Talk. It's so great to have you back, and I'm looking forward to hearing what you've got to share with us and everybody today. So Johan is an AI engineer, and he's a product owner at Imagimob. He's got a lot of experience in R&D projects, PhD in numerical fluid mechanics, which I'll tell you, I've seen the slides and there's some impressive math equations on there. So look out for that. Be prepared by the math that you're gonna see in this presentation. And MSc in engineering physics from Uppsala University. So Johan, I think it's all you now. And I'll hand it over to you. Please ask questions in the Q&A box. We're gonna have lots of time for questions. And I'll let Johan give you a little more information about the giveaway and start his preso.
Thank you very much. So you hear me good? And
yep, I hear you great.
Yeah, great. Thanks very much for the introduction, and yeah, I'm very glad to be here again to get this invitation, and nice to see so many listening. So yeah, I will let's see here. Just short about Imagimob. I will start here. So we were founded in 2013 with the idea that edge AI and TinyML is going to become big, and the field has certainly grown since then. And By TinyML, we mean machine learning models that can run on embedded hardware, like ARM microcontrollers that we typically use in our projects. And we provide our TinyML platform as a software as a service. It is a desktop application currently supported on Windows. We also provide our expertise in TinyML bundled together with the application as a service. We have experience from many customer projects, and it is that knowledge from these projects that we build into our product. We're active in TinyML events, and we are in the committee for the TinyML Sweden group, where we select speakers for TinyML talks. And we are the sponsor of the TinyML Foundation. And with this, I would say that we are an important voice in the TinyML community, where we help to shape the future of TinyML. We're based in Stockholm, Sweden, the capital of Sweden, and we are 15 employees at the moment. The agenda for today, after a short intro where I will present what we are doing and what we're offering, I will dive into quantization, which this talk is about. It's about quantization of neural networks. That is the core of our platform. I will start out with some basics to explain what quantization is and why we need it. And then I will explain what post-training quantization is and full integer quantization, how it can be implemented and how we can get it to work in the end. At the end, I will show how we can quantize neural networks in Imagimob AI. But first, just introduction about Imagimob AI. Our vision is simple. We want to simplify the development of embedded AI because developing small and efficient machine learning models alone requires some skills and expertise. But if you on top of that adds the development of embedded software, the task becomes very complex and time consuming. That's our experience. But with this tool, we want the application engineers out there to focus on their skills and on the application they want to build, not having to learn the details of machine learning and low-level programming. So as you can see here on this bar, the tool takes the user through the entire process from data collection, data annotation, model building, and evaluation of generation of C code that you can integrate to your firmware. And as I discussed in my previous ARM tech talk, we have chosen the track to generate plain C code out of the trained models. And this has many benefits, for instance, flexibility, portability, and speed. But with that being said, I should also say that we have some interesting and very promising partnerships where we can actually choose to output something else. We can choose to output binaries for a specific neural network hardware accelerator. So yeah, that's short about the vision. So it is a general development tool for TinyML applications. We support integration of many types of sensors like accelerometers, gyros, thermometers, etc. And the primary project types we support are classification and anomaly detection projects. But we have also decided to go deep into certain verticals like human activity recognition, where an example is the Bell-Pal watch that you can see here. It's a watch with built-in fall detection. And we have also worked a lot with radar technologies, we have built a fully functional prototype of gesture-controlled in-ear headphones together with OSM Group and Acconeer here in Sweden. So Acconeer, they manufacture this tiny radar chip that OSM Group helped to build into the earphone, and we built the software, the machine learning algorithm inside Imagimob AI. Audio is another application we have gone deep into, where we have typical preprocessor layers to build efficient audio models. And recently we created starter projects that makes it easy for the user to get started. So we have built-in data and pre-trained models and documentation that will help the user to get started. So that's short about Imagimob AI. And now I will go into quantization of neural networks. And that's a work we started around 1 year ago. So I mentioned it in the last talk, but since then we have done a lot of progress. The development started as a customer request to support quantization of LSTM layers that was not supported in any other framework at that point in time. So we decided to dig into it and deliver what the customer wanted. And I want to make this topic interesting also for people without so much knowledge in neural networks and computer science. So I will start out with the basics. So let's start from the very beginning. How do digital computers store and manipulate data? Because that, if we understand this, we understand why we need integers when we run on the smallest MCUs. But this will come in a while. Let's start here. Computers represent data in sets of binary digits. And 1 bit is the smallest possible piece of information represented on a digital computer. And it represents one of 2 states. So it's basically a small switch that is represented by an electrical voltage or some electrical state in the hardware. And this is the reason we use the base 2 system to encode information, since we just need these 2 states. If we group 8 bits together, we get 1 byte of information. And let's see how this byte can take on different values. If all bits in this byte are turned off, they are, all the switches are turned off. We get 0, since with the base 2 system, each digit represents a base of 2 and an exponent of 0 up to 7 if we start from the right. And this also means that if we turn on the last bit here, we get 1, because then we have 2 to the power of 0, which is 1. But if we want to have 3, then we get we turn on the last 2 bits. So with an 8-bit integer, we can represent 256 values, because it's the combination of all these. With a 16-bit integer, we can represent 65,536 values. This is what happens under the hood of these integer representations. All right, integers are great, but decimal numbers are quite handy for us when we want to calculate something, like how far does the ball get after 2 seconds when I drop it. And it's quite handy to have decimal numbers, or floating point numbers, as they are called in computer language. And they are represented by in this way. So we have a certain number of bits for the sign, exponent, and the mantissa. The mantissa being the decimal points here, the decimal values. And if we have a 32-bit float, we use 8 bits for the exponent and 23 bits for the mantissa, whereas if we use a 64-bit double, we have 11 bits for the exponent and 52 bits for the mantissa. But the important thing here is that up here, adding and multiplying can be done using bitwise operations and shifting, and that's really, really fast. Whereas down here, multiplying and adding takes much more time to do. There are more cycles to do all these operations. And that's kind of the background. So to do floating point operations, what computers usually have is an FPU, a floating point unit. And all modern PCs, smartphones, and tablets, and powerful microcontrollers have this included. So, for instance, the ARM Cortex M4F, M7F, and M55, they have an FPU option, whereas the smallest MCUs, the M0, M1, and M3, they do not have an FPU. Here we can see an example of an M4F. It's a Silicon Labs Wonder Gecko board, whereas here the Arduino board, this has only an M3 core. And what options do we have then for the smallest MCUs? Well, we can emulate floating point operations in software. So we do these operations in software. It takes at least 5 to 10 times more time. So we waste a lot of cycles to do these operations. Another option is then to transform the data to integers and do the calculations with the integer arithmetic. While we're doing that, we can also choose to use 16 or 8-bit integers, and by doing that we can save some RAM and flash memory. But yeah, that's an option. But this transformation requires some thinking and care, otherwise we will get a large quantization error, and that's the yeah, what I will discuss more here. So now we know why we need quantization for the smallest MCUs. And to perform the actual quantization, we have two primary options. And one is to define the model, the neural network itself, using integers already from the start. So we do the training and the inference using integers. This is called quantization-aware training. This has its own complexities and difficulties. Can be difficult, for instance, to get a model to converge during training. What we also can do, another option, is to use post-training quantization. And here we define the model using floats. We train the model with floats, but then afterwards, when it's trained, we quantize the model. And there are many ways to do this. We can mix integers and floats in various ways. What we will focus on here is, and what we have done is, full integer quantization, which has the best performance and accuracy if you implement it carefully and in a good way. But this removes all the floating point numbers from the code. So as I show here to the right, when the data comes into the model, we quantize it, so we transform it to integers, and then we run all the operations using integers, and then at the end we can dequantize the output data if we have the need for it. But on these small sensors, usually everything is integers anyway, and then we don't need to do this. Right, so how do you do this? The first step is to define a mapping between integers and floating point values, so a transformation between the two. Here I use an example where all the floating point values are between -2 and 5, shown here on the x-axis of this graph. If we use a simple rounding, then we get, this is just an example that shows you that if we're not careful, we will get a large quantization error. So you see this step here. The resolution is poor and all decimals get wiped out. But we can do better than this, because think about it, if we have an 8-bit integer, we have more buckets. So if we think of stretching out the y-axis here, we can get something like this. So much smaller quantization error. So you see that now we use all the available values for an 8-bit integer between -128 and +127. And we use a scale and the 0-point value so that we stay within these limits. If we don't do that, we get overflow and then we lose information. But one interesting key observation here is that we can choose these values as we like, as long as we respect these min and max values for the integer. And this is what we do in our backend. So we create functions that can change a scale value and keep the 0-point value, or vice versa, or keep one endpoint and change the other, etc. And this is important to note here. This is our way forward in this to solve the problem. Okay, so now we have the mapping ready. So what we now have to do is the following steps. So let's find the scale and 0-point values, which we call the quantization parameters, and then we use those to transform the input data, and then we also have to define some quantized operations, and we follow the idea in Jacobs et al., which is an excellent paper. So we transform all our add to become a Q add, and our mul to become a Q mul, meaning a quantized operation, instead of using integer values. So let's look at this by using an example. It becomes easier. So we will multiply two numbers A and B together, and we get the number C. All right, so then we use the quantize operation to solve for Ci, the integer C here. So first we just transform the left-hand side and the right-hand side, and then we solve for the integer C. So if we do that, we get this expression, and as you see, the scale value, I just multiply scale A and scale B together. So remember now that all the values in this expression are supposed to be integers. So we can observe that if the remainder in this division is not 0, we will have an error, and that's exactly the quantize error that we will introduce then. But if we set the scale AB to be equal scale C, for instance, we will have a zero error after this operation. So now you start to realize here that if we're clever, we can set these values, manipulate the values so that we get a reduced error. And to see how this quickly can become a bit complicated, we add a second operation after our first multiply. So let's add another scalar to the result D, to the result C. So C plus D becomes a new number E. Again, we use the mappings we have already defined, and now we solve for the integer version E here. And what we can see is that this expression has dependencies in the scale values from all previous expressions. But if we set them to be equal, we can simplify the expression, and because then we see that they are actually canceling out. But then we have to set them equal, so that's another requirement. And if we also set the 0 points to be 0, we get a very simplified expression here. So it's just an addition of 3 integers, and no error is introduced. But this means that we have to fulfill this requirement that we have set up. And by noting down all these requirements, we get a system of equations that has to be fulfilled. And in this small example, it looks like this, but in a real model, the system will be much bigger. But the thing with this system is that it's a hard problem to solve. It's often overdetermined, which means that it's an optimization problem, and often the round operator is present, which makes the problem nonlinear. And the solution of the system are integers, which altogether makes it a really difficult mathematical problem. So what we do is we use an heuristic approach to this. It may not be the optimal solution, but we can most often find a solution with a small enough error. So what we do in an automated way is we go through these steps that I will show you here. First, we generate normal floating point C code. Then we feed some training data or validation data through the model. We record the min and max on all the buffers and weight matrices, etc. We also record the expected output. Using these naive quantization parameters that span the whole width, so to speak. So we use those values, but then we go over the compute graph again, and we check all the operations and their quantization contracts. And then we sort according to if the contracts are required or if it's just accuracy. And we figure out which sets belong to each other. For instance, if A equals B and B equals C, then A equals C, and so on. So we do a lot of these things under the hood. We set new scales on the tensors, so that we fulfill the contracts, and then we quantize the model using these parameters. So we turn them into actual integers. And finally, we generate C code and we run a test with the quantized code and calculate the quantization error. So compared to the float code. So that's the theoretical background of what we're doing behind the scenes. And what I will do now is to train and quantize a model in Imagimob AI. So you will see how it looks like. And what I will do here is to take human activity test case. So we want to classify human motion based on an accelerometer mounted on a person. So we start out by creating a human activity starter project. We select here somewhere to store the project and the data. So as I said before, it has some example data available. And there's also some documentation, how to use the project and what it contains. And here on the data tab, we see that data is already imported, and we can just double click on a file here to see it. Here's, for instance, a file with some jumping data. We can play it through and look at the labels, how they are located. And then we have some, I guess, yeah, this is some running data. And here we also have a video attached, time synced with the data, so that it's easier to label the data. Right, so in the classes tab here, we see the output classes, and we can change the weight of the classes to make the model more sensitive to certain classes if we have less data for those, for instance. In the preprocessor tab, we can add custom preprocessor layers. In this case, the data is quite simple, so we just add a sliding window that collects data in chunks and feed it to the network afterwards. Now in the training tab, we generate a set of models, and yes, some of these models have LSTM layers that we can see here, for instance, and they have the input size from the preprocessor, and the output size is the number of classes. The output neurons is 6 in this case. So here we press start training job, and then we will send this job to the training server. All right, so that's the first step to get trained models. Next, when the model has the job has finished, we can see this green check mark. We can see the accuracy, F1 score on the models, and we can sort them according to the best model, etc. And then it's time to download. And here what we download is the trained H5 model itself, but also the model predictions and the input and output data for the compare test that we will perform later on. Right. So here I have downloaded this to my local computer. And here we have the predictions. And if I double click on the model file, I will see the architecture, and I can see the evaluation. And here, if I go to the Edge tab, then this is where I convert the model to C code. And I select here ANSI C code and somewhere to store the output. And here I have the option to quantize only the network or the network plus the preprocessor. And this is what I will choose here. Here I select some representative data from which we will compute the min and max values that I talked about before. And down here we set the tolerances for the quantization test. Okay, and down here, this is the where we select input and output files for the Python compare test. So this is to compare that the C code that is generated has the same output as the trained Python model. And then finally, we click Build Edge, and this is right. So here we generate the normal float C code, from which we collect the min and max statistics. And now we also generate the output for the quantization compare test. This will take a few seconds here. And what we're doing now is that we perform the steps I explained earlier, where we set the min and max and the buffers and go through our contracts. And this will also take a few seconds. Yeah, and then we run through all the test files to compute the quantization error. And finally, also we do the Python compare test. And we can see that our tests passed. Good. Okay, so now we have generated some C code. And it only has floating point buffers for input and output, and it's easy to integrate into the firmware on any ARM Cortex series MCU, even the smallest ones. The only calls that needs to be added are calls to one call to initialize the model, one to enqueue data into the model, and one to dequeue data from the model. And here I have a code snippet where we see the queue function, where the LSTM cell is called 16 times. And to the right here, we see all the operations that are needed to perform one of these LSTM cell calculations. And as we can see, there are many calculations, and as you can picture yourself, we need to have the quantization has to be low here, and yeah, so that's the balance in all this in this game. And we have done performance test using a long chain of LSTM cells, and we have seen that the speed up is around 6 times. Running float code versus quantized code on an MCU without FPU. But when we have the FPU on the MCU, the performance is roughly equal, and that's expected. I mean, if we have an FPU, then this is unnecessary. This is the takeaway here is that this is needed for the smallest MCUs without an FPU. And so yeah, that's my last slide.
Thank you so much, Johan. That was very, very, very interesting. I don't think you could get a better university class describing in detail how this stuff works. So thank you for sharing that. We do have some questions that have come in. So let's get to a few questions. And no, we did not forget about the giveaway. So shortly in a few minutes, we'll be posting a link where you can enter to win 10 Dialog IoT multi-sensor board, which is pretty amazing sensor. Actually, I was looking at it. It does have a Cortex M0 in it with no FPUs, as we learned today. The Cortex M0 does not have FPUs. So in a minute, I will paste the landing page where you can go in and enter for one of these boards that Imagimob is giving away to you guys for free. So let's get to the questions. Let's see. Just general from Farine, what is your opinion on the performance of quantization-aware training? Generally, it often results in low accuracy with some models and data sets.
Yeah, quantization-aware training, I think it's a great idea. We don't have so much experience in this. We read a few papers before we started out with some strategy, and yeah, we went for the option that seems to be yeah, easier. So I cannot say too much about quantization aware training,
Sure.
but I guess it's great if you get it to work. But yeah.
Yeah. And is another quick question, is quantization of the model after training possible?
After the training, yeah, that is post-training quantization. So that's what I described here.
Cool, great. And how robust is a quantization strategy to new data that may not be represented in the typical data set used in the algorithm?
So yeah, so I would say try to get representative data in there.
Yeah.
That makes it much better, because if we get some strange data out here, then we may not have been able to adjust the parameters to that data, and then we can get some overflow, and we lose information.
Yeah. Okay. Yeah, these questions, thanks so much everybody for these questions. So let's see if we can get through them all in the next 5 or 10 minutes here. Satyapreet is asking, is full integer quantization equal to quantize aware training?
No, both approaches have only integers. But in the quantization aware training, you start out with integers, you do the training with integers, everything like with integers. But in our case here, we do everything after the training has completed, but we still have everything in integers. But there are other variants where you mix integers and floats, and yeah, you can do all kinds of things, but we have focused on the purest way to do this, because we want to get rid of all the floats,
all the noise. Manuel's got a couple questions. So clarification is a quantization error, is it the error of the inference due to quantization, or the information loss on each tensor due to the quantization?
What was the first thing you said?
So I think he's asking if it is a quantization error, is it the error of the inference due to the quantization, or is it due to the information loss on each tensor due to the quantization? So I think he's trying to understand where a quantization error might occur and why.
Yeah, so exactly, it's a good question. It occurs because when we have all these all these parameters that we set on the tensors, the mappings on the tensors, then sometimes we're not able to find the optimal parameters, and we will have some rounding there because we have integer operations, so we have to do some decimals are disappearing, and that is the quantization error. So I don't know if that's an answer, but yeah.
Yeah. I think that's as close. Manuel, pop in the Q&A box again if that didn't quite answer what you were your question was.
But yes, so maybe to clarify a bit more, when we compute the quantization error, that is the difference between if we would run the model with the floating point operations and floating point data, and then we quantize the data, run it through the quantized model, and then we check the difference, and that's that's the quantization error.
Great, thank you. I know it's dense to try to explain this stuff, so well done on that. So just for everybody, I just put a link in the chat. If you click on that, that should take you to a form for a giveaway of the Dialog IoT multi-sensor. So have at it. Good luck. They're giving away 10. Next question on slide 14 and slide 18. How do the outliers affect the quantization process? For example, the min and the max of all tensors. Is this addressed? Any comments on robustness?
Let's see.
They said slide 14, yeah.
14, is that maybe, is it this one?
Yeah, I think so. It's got just a question about how outliers affect the quantization process. Yeah, that's slide 14. Yep. And it also referenced slide 18.
Right. Okay. I see. Yeah.
Yeah.
That is a problem. Right. Exactly. Because that make so basically what the question is about is that, okay, most of the data is here, so we would like to focus all our buckets around this data here, but then we have one here, so we have to stretch out to this one, so we will get a worse resolution. And our solution to this problem is to work with the pre-processing to try to put the data together. It could be simple multiplies and things like that, but more often we work with FFTs and so on, which usually puts the data together.
Okay, let's see. Sorry, it looks like the link I posted is having some issues. I'm going to try to fix it. Let's go to the next question. So do you support quantization lesser than 8-bit?
Well, no is the answer right now.
Easy enough.
But it wouldn't be hard for us to put it in, but we haven't really, we didn't need that so far.
Okay. And then another question is, what benchmark apps have you tried on this? Have you tried MLPerf 0.5, for example?
So what was the question? What kind of?
Just have you tried any benchmark apps? Have you tested the performance on, you know, like a public performance like MLPerf 0.5?
No, we had our own tests on this
Okay.
Yeah.
Yep. Let's see. And then really quickly, where do we find function definitions? For example, the QCon1D underscore S16S16.
Like I showed in the end, perhaps.
Yeah, exactly.
So the question was, where do we find it?
Yeah, the definitions for those functions.
I see. Well, download Imagimob AI and quantize the model and generate C code, and then you will have it.
Speaking of how would people get a hold of the Imagimob Studio? Do you have an eval license or a trial offering that people can sign up for and use? Would be great.
If you go to our webpage, our homepage, you can sign up there for a free trial. It's 30 days.
Great.
Trial that you can use. Yeah.
And that's imagimob.com. Let me put the link in for everybody here to make it handy and easy. Okay, and then while this is getting loaded, here we go. Let me put this in the link for the chat for everybody. Okay, I think we have time for just a couple more questions. So let me scroll through and find these here. Let's see. Regarding the slide on the full integer quantization, do you have any references on the techniques to handle outliers?
The slide of the full.
Yeah, so I think back on that slide 14 with the outliers, is there any kind of reference or a technique on how to handle these outliers?
No, I don't have any. No, it's
okay.
No. But yeah, like I said before, we work with preprocessors, and but yeah, it can be a problem. We have seen that.
Yeah. All right, couple last questions. Are you planning to generate other types of binaries or formats as output in the future?
Yeah, that's a good question. We went for the C code path already from the start. That was actually before any other types of binaries or frameworks existed. And yeah, we've heard from embedded programmers that it's a nice thing to have access to the C code, but we also have these interesting partnerships where we generate other types of binaries that fit into the some neural networks accelerators.
Great. And lastly, since I think we're pretty much out of time and we'll let everybody get on with their days, is can you convert can you convert models from other frameworks to C code?
From other frameworks, so currently we support TensorFlow formats, but yeah, that's what we have at the moment. PyTorch is something we may support, but yeah.
Great. Okay. Well, Johan, this was great and very, very, very informative. Really, really thorough explanation of quantization. This is I probably will have to go back and watch this again so that I can really like understand some of the concepts that you spoke about. But thank you very much for, yeah, you have to look at it again too. And you do this stuff. It's hard. Machine learning's hard. I think, you know, it's something that we all are trying to make easier for people, but really it's hard. So everybody doing it out there, you know, just keep at it. It's you know, with tools like the Imagimob Studio and these things that are available now, it's made your jobs a lot easier, that's for sure. So
yeah, I know. And it's so many different aspects of it. It's not only the machine learning itself. I mean, the quantization is an old topic, let's say.
Yeah, for sure.
But we combine different things now, and yeah, so it requires skills from all over the place.
Yeah, definitely. So please, everybody, feel free to, if you have questions, you can contact Imagimob directly. I've put their website in there. If you want to dig in and try out their tools, sign up for their eval license, and you know they build this stuff. They know what they're talking about, so they will help you with your projects. So again, Johan, thank you so much. It was so great to have you here. Can't wait for the next one. Anders, it was great to have you here as well. And everybody have a wonderful day and evening. Check our YouTube channel for the replay of this. And we will see you back here again in 2 weeks at our next virtual tech talk. Thanks, everybody. Bye.
Thanks.